Welcome back to Chem 4300. In this video, we're going to continue Chapter 18 on the electronic structure of the hydrogen atom. And we're going to pick up where we were last time, where we had taken the problem of two particles, the electron and the proton, the hydrogen atom, and separated it into the wave equation for the center of mass and the wave equation for the relative motion of the electron relative to the nucleus. And now our focus is on this potential energy function, which is the Coulomb interaction, the attractive force, which is a central force. And what we want to do is rewrite that problem in terms of spherical coordinates, because it's the more natural way to look at a problem with such a spherically symmetric potential. So here is our wave equation that we have to solve. And here is the potential. It's a Coulomb potential. It goes to minus infinity when r goes to 0. So when the electron approaches the nucleus, this potential goes to negative infinity. And when the distance between the electron and the proton go to infinity, then the potential goes to 0. So this is the maximum in this bound state. The maximum potential we have is a potential of 0 when they're infinitely far apart, and the lowest potential is minus infinity when they are exactly at the same spot at r equals 0. So this is the form of our potential. These are where the solutions for the eigenvalues will be. We'll come back to that later. And let's take a look at then how we're going to take this potential, which is spherically symmetric, and let's take this Laplacian, convert that to spherical coordinates, and re-express this wave equation in a form that should be easier to solve. Now, that may not look easier, but this is a formula that we've seen before. We've looked at the Laplacian in spherical coordinates, so it's not completely unfamiliar to you. This is what it comes out to be. So that's just taking this Laplacian, expressing it in terms of spherical coordinates. And now we also even recognize this part here, which just has the angular dependence, as related to the total angular momentum operator squared. So we can now take this form of the Schrodinger equation for the relative motion, and we can rewrite it in this form here, where we've taken all of this part related to the total angular momentum and we've moved it over here on the right. Okay? So this is the wave equation that we want to solve, and we have a solution that's going to depend on r, theta, and phi. Now, again, this is not a big surprise that we're going to use a separation of variables, and we're going to divide our wave function into two parts, a part that depends only on r and a part that depends on theta and phi. It's a guess. We'll plug it into this equation. If it works, then it was a good guess. So if we plug this into here and do a little rearranging, this is what we get. We get an equation where everything that relates to r can be on one side of the equality, and everything that relates to theta and phi will be on the right side. Now, this expression has on the right the total angular momentum, and we know the solution for its eigenvalues and eigenstates. We know that when the total angular momentum operates on the wave function, it gives back this eigenvalue, and these eigenstates are the spherical harmonics. So we can take this result, the angular part of our solution is already, of our wave equation has already been solved. We know it. We can take this result and plug it in here. So if I can take this term here, plug it in there, and then do a little simplification, I end up with this differential equation here. So we now have an ordinary differential equation for the radial part, and it's equal to this separation constant over here that we get from the eigenstates and eigenvalues for the total angular momentum. So that's a big simplification. We've taken the problem now, we've gone from the center, from the total system down to the relative motion wave equation. We've taken the relative motion wave equation and we've converted it into just the radial part wave equation, and this is where it now starts to get a little tricky. So this is what it is if I rearrange it. And this looks like H psi is equal to E psi. So this is the Schrodinger equation in one dimension, and this is what our effective Hamiltonian looks like. And if you look at this, you see that this part is related to the kinetic energy, but this part now is what looks like an effective potential. So we still have our Coulombic interaction, which will go into here. I haven't put it in here yet. But now adding to that is a new term we get by going into this picture where we have eliminated the angular parts and we're looking at only the one-dimensional Schrodinger equation. And this acts like a centrifugal term. In other words, as the electron's orbiting around the nucleus, if we're looking at the radial wave function, that this term here will act in a way that looks like a potential energy that's pushing the electron away from the nucleus, while the Coulombic interaction is pulling the electron towards the nucleus. So notice they have opposite signs. So they're acting against each other. The more angular momentum you have, the more the electron wants to be pushed away from the nucleus. And the less angular momentum you have, then the dominant Coulombic interaction will pull the electron towards the nucleus. Now I'm going to go ahead and plot this for you. And I'm going to plot it in terms of the energy as a function of r. So here it is. This is the energy as a function of distance. And I'm going to put these in atomic units. So I'll go back to this in the next slide here and tell you that this is what's called the Hartree. It's an atomic unit of energy. And this is called the Bohr radius. It's an atomic unit of distance. But nonetheless, you can see what the energy versus distance looks like. And for L equals 0, the quantum number that's associated with no angular momentum, we can see that we just get the Coulombic interaction. The electron is strongly attracted to the nucleus. But with L equals 1, we see that the Coulomb interaction works for a while, but then the angular momentum of the particle causes it to be pushed away, and it looks like a repulsive force at that point. Similarly here for L equals 2 and L equals 3, we see that the higher angular momentum, then the stronger this centrifugal force that's pushing the electron away. Now, the one thing I want to go back to is these atomic units. We're going to be using them over and over again. So the atomic unit of length is called the Bohr radius, and it's given by these constants here, which you can look up and multiply out, and you'll get this distance of 52.9 picometers. And that will be used in a lot of the problems we'll be working with as sort of a scaling factor for distances that convert us into dimensionless lengths, so to speak. And then for the atomic unit of energy is going to be involving the Bohr radius. It's going to be given by this expression or this expression here. Either one will give you the same number, which is 27.2 electron volts. And so for looking at this problem, oftentimes we may be scaling it with respect to the atomic units of energy, which is called a Hartree, actually. Okay, so that's it for this video. In the next video, we're going to look at solving that radial wave equation. And this is where it's going to be pretty challenging. All I want you to do is just try to follow the logic. I do not expect you to be able to solve this kind of wave equation on your own.